just formally announce the start of this Oxford workshop on Homotopy Type Theory. Thanks everybody for coming. And our first speaker is Benedikt Ahrens, and he'll talk about univalent folds, and he is currently from the University of Toulouse. I'm sorry, Benedikt. I have to ask. There are two more things. First of all, there is a change in schedule. I don't know if everybody heard about it for Monday. The rest of the schedule remains the same, but for Monday there is a change. And the new schedule, the new program is probably not yet online, but it exists in a printed form and can be seen on the door of this lecture room, and also over here for those who want to pick up the printed form. The second thing is that there were some adjustments to who will and who will not come to the dinner tonight. So I think we still have, at the moment, two spaces at the dinner, which was announced as being sold out. So if anybody is interested, please talk to Kobe over here. He'll keep track of things. Thanks.
So I will talk about univalent folds. Is this big enough for everyone? This is joint work with Page North and Mike Schulman. And it's also very much work in progress, so I will just give some ideas. I will talk about work that's not by us and then explain or sketch a bit how we try to extend it, but this is not finished work. So I'm going to give a quick table, a short table of contents. The motivation for this work is the equivalence principle that I will explain. And then I will explain work by Makkai that is called Folds, which implements this equivalence principle. And finally, I'll then explain how we would like to adapt folds to our purposes, namely folds in univalent foundations or folds in infinity-groupoids. And since this is the work in progress part, so there is not much to be talked about here yet, but I will then just go through an example of what we would like to do here, the example of categories, and explain this here using this example. Univalent folds by example. Okay. Oh no, this is not.
No, it's just by hand.
Just by hand. Okay. Wow. Okay. So, what is the equivalence principle? It's an informal principle that says that reasoning in mathematics should be invariant under an appropriate notion of sameness or of equivalence of the objects under consideration. Okay. So, the equivalence principle, reasoning. Should be invariant under equivalence. this principle in mathematics is not enforced. For instance, we can easily break this principle by just, well, let's just consider two categories that are equivalent. And it's very easy to make a statement that is true for this category, let's say, and false for this category. For instance, the statement category C has exactly one object. Okay, so this principle, it's not enforced, but we would like to restrict our attention to those statements that are invariant under equivalence. So, if we stay with the examples of categories, what are the statements that break invariance? They are exactly those statements who refer to equality on objects, in some sense. Okay? So, for categories, breakage, I just won't say that, I don't know. Comes from equality on objects. But how can we restrict our language, like the language which we use to reason about categories, to not use equality on objects if already the definition of a category actually refers to equality on objects? So first the problem is that even the definition of composition, for instance, in a category, we have the composite of G with F is defined if the target of F is the same as the source of G. Okay, so even the definition refers to equality. The definition of category refers to equality on objects. To circumvent this problem, one can introduce a language of dependent types in which such information about source and targets of arrows are actually encoded via typing information for G and F. Okay? So to fix this, we can use a language of dependent types. And what does it mean? I will give a definition of category that uses the language of dependent types, and you will see that I will never have to refer to equality on objects like I did here. So if I use this language, then I can define a category to be given as a collection O of objects. And then, now the next step is the important one. I don't have one collection of arrows, but I have a family of collections of arrows, namely a family parameterized by pairs of objects. Okay. So for each two objects x and y, I have a collection AXY of arrows from x to y. And now the definition of composition is simply a family of functions for composition for each x, y, z in O, and then arrow. Now I take two arrows that have compatible types, an arrow from x to y, and an arrow from y to z. And then I have the composite that is an arrow from x to z. Okay, in this way the typing information encodes the conditions on source and target. Some stuff missing. Okay. So if we add to this language that I have introduced here as a language for categories, and if we add some more logical connectives, to reason about categories and functors and so on. And this idea of expressing a category in this, or the definition of a category in this language is very old. There's a theorem by Peter Fried from 76 and long 78 was basically the same result, saying that if a statement about categories is invariant under equivalence of categories if and only if it can be expressed in this dependently typed language that I have not fully explained. Okay. This is everything I want to say about the motivation, about the equivalence principle. I will get back to the table of contents. Next point is Makkai's work on faults. The goal of this work, of Makkai's work, is to extend, like, go back to this. This theorem is a theorem not only about categories and the equivalence of categories. The goal of Makkai's work is to extend this theorem to other categorical structures. So what does faults mean? It stands for first order logic with dependent sorts. I said types here, I said sorts here, but they are used synonymously in what follows. Okay. As I said, the goal is to extend this result. To higher categorical structures. So there are basically four ingredients. That I will discuss one after another. Well, let's start with 0. The first ingredient is, I've already discussed, it's dependent types, the language of dependent types. Then the first thing that is new compared to this work is that we will also express operations via dependent types. Then, since Makkai not only talks about a specific structure, namely categories, but about arbitrary structures, we need a notion of signature. And signatures in this work by Makkai are given by one-way categories. And finally, there is a notion of false equivalence, of maps between structures of such a signature, under which there will be, for which we will have an invariance result. about operations via dependent types. I've given this definition of a category earlier, where we have the objects. We have sets, arrows, and objects and arrows. And then we have operations given by functions. Okay, composition is a dependent function, and Makkai does it differently. He expresses such functions via predicates. So the definition of a category in Makkai sense would look as follows. So, example, categories. A category would be given by a collection O of objects and a family of collections A, X, Y, as before. But then composition would not be given by a function, but by a predicate on triples of arrows. So for X, X, Y, and Z are objects, and F, G, and H are arrows of suitable type. So if F, G, and H are arrows like this, then a category is given by a family of assertions, in particular assertions T of F, G, and H, where T of F, G, and H is the set of assertions that H is the composite of G and F. And similarly for identity, we do the same thing. If we have F, an arrow from X to X, then I of F is the set of assertions that F is the identity on X. Okay. Okay, of course, I need a couple more conditions on T. For instance, I want to have the composite to be unique. So if I have T1 and an assertion that the composite of F and G is H1, and an assertion of the fact that the composite of F and G is H2, then I would need to know, and I would like to have that H1 equals H2. Okay, so this is uniqueness of composition, and I also need existence. And a couple of conditions for that the identity does the right thing. Okay, I will not write everything down. Now the point is that I made a big mistake here that I'm realizing now, but it's a good moment to fix it. So what is important here, I actually messed up the whole the punchline, let's say. The statement about categories is invariant under equivalence. It can be expressed in this dependently typed language. And what I need to say here is that in this language I may use equality on arrows but not on objects. Okay. So we need to somehow restrict the use of equality. And for that, first of all, we have to make it more explicit, say. And this is why we don't want to use here this kind of given equality where we don't know where it comes from, but we want to add to this definition of category equality of arrows as an explicit relation. Okay? So there are a couple of things that I haven't written down. But we also want to have if f and g are two parallel arrows. We also want to have a collection of assertions that f is equal to g. Okay. Now we modify this definition. Where do I have to modify it? Here. Here, instead of saying h1 equals h2 modulo this equality, I will say that they are equal modulo this relation. h1 and h2. I want E to be less like an actual equality, so I need a couple more assumptions about this relation, namely that it is a congruence with respect to T and I. And I need it to be an equivalence relation. Okay. Here I use the word relation, but there is nothing that ensures in this definition that E is actually a relation. Okay, so that there is nothing that says that the arrows from E to the arrows down are jointly one. So, yeah.
I would eventually.
Sorry?
The arrows. Last sentence. Could you?
So,
Nothing says that.
nothing. So I have. If I write it down like this. There is nothing that says that that these arrows should be jointly monic.
Well, so you would
But you don't have
get logic.
equality, so you can't say that.
Yeah.
Yes. I mean,
It's just not possible to say.
it will turn out that also the models that we consider for this stuff will not be models where we have this condition. Yeah.
One interesting thing about Mackay's language, right, at the term level, there are no compound terms, there are just variables. Right, so definition of equality is pretty trivial, it's whether one variable is equal to another. Because everything is predicates, there are no compound terms.
Yeah,
That's quite nice.
okay. So this is how Makkai expresses operations via dependent types. The second point, if I go back, maybe I should leave this here and continue over there. The second point that I want to discuss is the notion of signature. One-way categories. And also here I will just talk about this example of the signature for a category. So a signature, the purpose of a signature is to specify a dependency structure. So here we see that the collection of arrows that depends on the collection of objects and so on. So this is, and the predicate T depends on three arrows that themselves have a certain dependency on what their source and target should be. So we can express this via like in the form of a category, where the objects of the category represent the kinds of the kinds that occur, and arrows of the category indicate the dependency structure. So category is specified by the following one-way category. We have an object O, stands for the object of the category. We have an object A and two arrows that stand for source and target, okay, for the two dependencies of A on O. We have a trinary predicate on the arrows, stand for composition. We have a unary predicate I and a binary predicate E on the arrows for equality. And these arrows are subject then to further conditions. For instance, going this arrow and then like the pointing, like choosing the first of such a triple, and then taking the source of the arrow should be the same as choosing the last arrow, and should have the same source. Okay, so there are a couple of equations that must hold. Okay.
So you don't make any difference between these T, which are like collections of sets, and the predicates. Yeah? I mean, I would think A is a collection of sets, and T is a predicate, but a
T is also a collection of sets. Yeah. Exactly. So there's no difference, and I call them predicates, but they are actually just sets of assertions. Yes. So if I have this notion of signature, now I want to know what the models for such a signature are. So if sigma is a one-way category, I should say what a one-way category is, maybe.
Yeah.
Actually, so I'm still confused.
It's a useful thing.
Yes.
So, yeah? You say you're in predicate logic. Yeah? So what is AXY? Is it and what is TFG? Is it a predicate or a sort?
This is a sort.
So why can you write? So how do you write this expression there for all X, Y, Z, for all F, for all G, and then there is this sort? Or you assume there's an element of the sort? Okay.
No, this is just assuming the sort itself.
The sort exists.
Yeah, but
if
the sort appears in a predicate, what does it mean? I mean, you write a statement in predicate logic, and then the sort appears. Not making sense? I mean,
No, this is just an introduction for yet another sort.
Uh-huh.
It's just exactly the same
Okay.
as
so it's an operation. It's an operation, yeah. It's just an operation. Where does the predicate logic come in then?
It's not even an operation, it's a sort. Operation appears down there, where existence of composition will be a thing which will introduce an object of this sort.
Mm-hmm, mm-hmm.
This first line is just setting out the dependency of the sort in the predicate logic before then putting the predicates together.
Which the signature on the right
this would be the thing to say. Then if I have in this context, T blah 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 is a sort, and then I need a rule that gives me the actual existence of a composite.
The problem I had is that you write somewhere, let's say E X Y F G, in a. Is this then a statement in the logic, or is this just a sort? I mean, where does the logic come in here at all, actually?
It doesn't.
It doesn't. There's no logic. Okay, fine.
I mean, until now there is no logical. I must put a layer of logical connective.
Okay.
So to continue this, so how do you state the existence of composition?
I would say if I have f from x to y, g from y to z, okay, I've left something out here, then let's say that there exists some t, something, I mean, at a term depending on this input. No, I need to say, well, I need to have an arrow. There exists some.
So in practice, you'll have to specify this composition.
In practice, I will have to specify this composition.
And then just say that it's also comes together with an assertion that it's actually a composition.
Yeah.
But you don't have a term for me. I mean, on this, you have only variables. So you don't have a term for me.
I think the formulation
I'm not
is
quite sure
that it's for all f for all g there exists ht of fgh. I think that's how it's written.
So we do have predicate logic.
So then you have predicate logic.
I'm not quite sure. I'm not quite sure about how this syntax gets implemented. So what did I want to say? I wanted to explain what a one-way category is. So a one-way category satisfies two conditions. The first condition is that out of each object there's only a finite number of arrows like leaving this object. And the second condition is that there is no infinite chain of proper arrows in this category. So these two conditions ensure that the purpose of these two conditions is that to ensure that any sort, let's say, only depends on a finite number of input. Okay, finite input. So if I have a signature given by such a one-way category, then I can say what the structure of this signature is. And the structure is simply a functor from this category to the category of sets. Okay. And now to recover kind of this point of view, I need the notion of matching object. The matching object of, let's say, K is an object in sigma, and X is such a structure, then the matching object MKX defined to be the limit of all the arrows leaving K of X K prime. Okay? And of course I have a matching map, so I have a map from xk to mkx, and this is the map that he specifies the dependency. So, for instance, if this is A, then this is a map from A to O times O induced by, let's say AX to OX times OX, or category. So this map specifies the dependencies. And the fibers of these maps then actually correspond to these sorts here. Okay. So the fibers of the matching map are the sorts we have here.
Why X? So X is contravariant?
Sorry, I should note it like this here. I have X, A,
No, okay, no, okay, fine.
Good. So these are, this is the notion of signature and structures of a signature. Now we need maps between structures.
Sorry, the limit is excluding the identity, right?
Yes. So false equivalence. So a map of structures is basically a natural transformation. We're interested in particular maps. We are interested in those maps that are very subjective. Okay, so we have X and Y two structures. Then a map F from X to Y is very subjective. If all the matching maps are subjective, I'll explain what it is. So, what is the type of this matching map? We have a map from xk to, and here it is some yk. Oh, it's actually So this is, I will explain what it means. We have this pullback here, and we want this, all these maps, so this is the pullback. We want these maps to be subjective. This is the matching map. So what it just means in the case of categories, for instance, we want first of all the map OX to OY to be very subjective, and for any objects X and Y, we have a map from A X XY to A Y XY. This is not precisely not X and Y, but this is FO, where we have FO X and FO Y. We want all these maps to be subjective. Okay. And a false equivalence then is a span of very subjective maps. So false equivalence from X to Y is a span of very subjective maps. Yes. So with respect to this notion of false equivalence, then there's an invariance result by Makkai saying that any statement about a false structure that can be expressed in a dependently typed language, this is similar to the one that we had before, where we use equality only on the top level, like here we have an equality predicate only on the top level. Is invariant. Now I forgot how I started my sentence, but I will just write down the theorem. So, a statement about false structures is invariant under this false equivalence if and only if it can be expressed in a dependently typed language. With equality, with equality E only on top level. Okay, so one thing that I mentioned earlier, here I've used the word relation, and there's nothing ensuring that in such a signature here, that T, I, and E are actually mapped to subsingletons. Okay, so there is nothing. But Makkai says that, Makkai proves that for every such structure, I can always find, like, a given structure is always false equivalent to one where this is the case. So I can always choose a representative of a false equivalence class where I have the top level being just relations. Okay.
So what does it mean, only on top level?
On top level means that I have no arrows into these objects. This is the top level.
Could you explain why this notion of equivalence in the case of a category has anything to do with the usual notion of equivalence?
I can. You actually need only one. For categories you only need one sign.
But did you say that these things should be surjective?
Yes. So you get the notion of a fully faithful and essentially surjective functor.
Why is it faithful?
It is faithful because if you write down the condition for E, I'm not sure if it is the condition for E, but it's one of the conditions of the top level that ensures that it is faithful.
Okay.
Yeah, it's a good question. I didn't want to go into it, but yes, it is. There must be a condition for it.
And why is it essentially subjective and not just
It
subjective?
is subjective, yeah.
So you need the two legs of the span, don't you, to get to weaken it to essential subjectivity?
Yes. Right.
So what is E?
How do you do it in practice? So suppose you want to go from well, I don't know, from in that example of yours, which you start with. Okay, so you project in one direction and it will be subjective. Okay.
So, what is E? I mean, you specified E in this particular theory, but this statement seems to be about any signature, so I'm not really sure what is.
E means that you have an equality predicate for all the you may introduce such a predicate for all kinds that are on this level. This is kind of the top level here, okay? And you don't assign a level to these relations because they stand for operations. And then this is the top level, and you are allowed to introduce such an E only for this an equality, only for kinds on this top level. So if you had more stuff, if you had, I don't know, whatever, something else, an A prime here, you could also introduce an E prime here for this one, but you should not introduce an E prime equality for this.
And suppose you had A prime on top of A?
If you have something on top of A, then you don't talk about equality on A.
But you have I on
Yes.
top of A.
And T.
No, no is a predicate, not a sort.
I is a predicate.
No, yes. No, but
So they
Is what
really
chosen is.
yeah.
kind of names. I mean,
Go on.
some of them are called predicates.
Aha.
They're called
I
predicates.
was just told that's not the case. Now I'm confused.
No, but they don't have to be predicates, but they're called predicates.
Makkai is
I'm sure Makkai has a better, I'm sure he has made this precise, but I don't know.
So it's first order logic, right? So,
Yes.
so you have a first order logic of
Yes.
predicates without.
Yes. You have predicates and sorts, I would think. And
That's
O and A are sorts.
So T is a predicate. Right?
T is a predicate. That's what I
So
thought.
you can think of it as a sort where you're just saying there exists something in this sort. Like, and the predicate is that there exists.
But
something.
isn't it more the other? Okay. You have you have a predicate and you can turn it into a sort, or
Well, I think one of the key points here is that it's being formalized in code. So we should just ask Benedikt to explain to us how it is formalized.
This can't possibly be a good way to see.
I'm not sure.
This is actually one of the main points, that this distinction is kind of weird and unclear. But it will be clearer when we do the next step, when we replace set here by infinity-groupoids. Well, this would be the next.
just to try and check before the next step.
Yeah.
Am I right in understanding that as far as the logic itself is concerned, there is no difference at all between predicates and sorts? Predicates are just a certain kind of sort. But then for the statements about equivalence and what's invariant under equivalence, that's the point at which we distinguish some of the sorts and call them predicates, and then make statements that depend on which ones are predicates?
Yes.
And where did we use this difference between predicates and sorts?
Well, there is a dependently typed language that we associate to a signature. Okay. That I have not explained, but here in this dependently typed language, we have, we want to talk about equality only for these sorts.
Yeah.
Okay. So there, in order to define this dependent type language, we need to point out these kind of top level things.
There can be predicates, but it's still a top level sort because there are only predicates on top of it.
Yeah, I hope this might clear it up. In Makkai's book, I think from '95, there's no E, at least in the beginning. So you just look at this one-way category where you have things in the top level, everything is stratified, right? And the top levels are really predicates, and you work with predicate logic with those top level things as predicates, and that's how you formulate the logic. But then maybe later you can reformulate it in terms of these E things. But I mean, maybe that helps.
But can you use sorts as predicates?
No. You formulate the signature where the signature is a one-way category, and that distinguishes the things that have no in arrows that are the predicates, and the other things are the kinds or the sorts.
So the things which have no in arrows are predicates.
Yeah. And then you require that in a structure, which is this functor into set, that these arrows are jointly monomorphic. But otherwise, you don't
Arrows
have a structure.
from the top level things.
Yeah.
Okay.
Sorry, when is this required? Is it required
For the
that they are
predicates.
jointly monic?
Yeah. In Makkai's initial definition, where there are no E's, he always requires that the structure is such that the top level things are jointly monomorphic.
It starts out looking good and it gets worse and worse as it goes on.
No, I mean, in Makkai's definition of structure, it's definitely that this is not required to be.
There probably he has many definitions, but in the book, that's why in the book it's part of that definition.
Okay.
I don't know where you pull the book. There is an unpublished paper which is called Calls.
There's
It's
an
called
unpublished
False
paper
Applications
called
to Category Theory. It's about 200 pages.
Oh, yeah, and it's also reflected by.
And there is a paper that is called Towards a Categorical Foundation Mathematics. There's a published paper about this.
Yeah, I think this is a book draft. It is circa
Univalent foundations, we have a language of infinity-groupoids, so it makes sense to see what happens if we consider structures to be not functors towards sets, but functors towards infinity-groupoids. And there turns out that we need to assume some more structure on the functor. So in order to explain this, I would first consider again the example of categories. So what happens if we take a category and internalize it in the category of infinity-groupoids? Okay.
I hardly dare ask this, but I will. What's an infinity-groupoid?
An
Do you just
infinity-groupoid,
ring a cannon complex and it's a little set?
for instance.
Oh, it's the for instance that I don't really understand.
Okay, yeah. It's
Because at one point people talk about infinity-groupoids.
Oh, it's a
It's a
canonical
definite thing, and then at another they say, well, what do I get is can complexes? But, so there's not one notion.
There is no one known, but let's say canonical.
Okay.
Okay. So if C is a category, then we can look at its internalization in groupoids. And what is this? Well, it will be a diagram like this with a bit of extra structure that I'm not writing down, where O is the groupoid of objects and isomorphisms, and where A is the groupoid of arrows and isos. That means of unity squared. And the first observation is that if I have the functor f from C to D, then this functor is an equivalence externally if and only if its internalization is an equivalence of groupoids on the level of O and A. An equivalence if and only if f hat is a level-wise equivalence. Let's say C, OD, and AC, and furthermore, for such an internalized category, we have more properties. C hat has the following. So first of all, the map, the induced map from A to O times O has is a discrete vibration. And second, we have a canonical map given by lifting from Hom AB to ISO AB. And this map is an equivalent. I will explain what this map is. So Hom AB are the morphisms. So if A and B are objects in O, and Hom AB are the morphisms in O. And ISO AB in A are those objects in A which represent isomorphisms from A to B. So you can call any internal category that satisfies these two conditions a saturated category.
Little a with
Sorry?
little a with.
Ah, sorry, yes, sure. Okay, so definition. An internal category is called saturated if it satisfies these two conditions. Then we have a theory a statement or construction about saturated categories is invariant under equivalence in the language of, well, univalent foundations. Okay. So this motivates an extension of the definition of saturated for univalent to arbitrary form structures. So the goal is to have a notion of consider false structures in infinity-groupoids. And what we know that what we need is that these matching maps that we have here these maps must be vibrations. Not the matching map, but the dependency assigning map. Okay. So now there is a conjecture, and I think I'm done almost with my time. So I'll write down the conjecture, and then the last part would have been that I work out this for the example of categories, but I'll do it some other time.
Coffee break.
What's an equivalence?
Equivalence here? Or
Yeah. What is subjective?
what is subjective here?
Yeah, I mean, when you go from sets to infinity-groupoids,
Well, here we have a different notion of equivalence,
which
which should be a level-wise equivalence.
just a simple level-wise equivalence.
So that's the hope actually. I mean, the hope is that we get a simpler notion of equivalence. One of the hopes. And another hope is that we clarify the situation of the top-level things that they are. I will write it down. Okay. So for univalent or separated false structures, so the hope is actually that there is a notion of univalence for false structures in infinity-groupoids, such that the following holds. We firstly have the false equivalence is given by, or is level-wise equivalence secondly, that in univalent structures, the top levels are automatically sub-singletons or relations. And finally, that a univalent structure, for univalent function structures, E is equality.
And univalent is the same as saturated?
Yes, univalent or saturated. Okay, so I guess it's time for me to stop.
Questions or comments? Yes?
So, this reminds me on in type theory, when people formalize category theory, pre-homotopy type theory, they always had a setoid of arrows and a type of objects. Yeah? And that seems to be justified by this theorem because you never want to talk about equality of objects, you only talk about equality of morphisms, right? The problem I always had, I mean, the statement that you made in the beginning is a statement about one category, right? But if I do category theory, I usually talk about more than one category, right? And for example, when I construct an arrow category, I turn morphisms into objects. And then, how does this work? I mean, if you never talk about equality of morphisms, how can you turn morphisms into objects?
No, that works quite well.
That's the right way around.
Oh, the other way then.
It's the other way around.
Okay, the other way around, yeah. When you want to talk, when you talk, arrow category, you talk arrows into objects, that's it.
Yeah, and then you
Then you
don't
lose
talk about
equality.
equality of arrows anymore.
Fun?
And you
Then you don't talk about equality of arrows anymore.
Yeah, but then
It's a
two
fundamental
objects,
category.
which were two morphisms which were equal before, should be still equal when they are objects, right?
Yeah, but you just don't mention it.
But a functor category, I think, is where that kind of problem does come up.
Yeah.
Well, if you want to form a functor category,
right?
exactly.
Notion of what?
And a functor is Mackai's answer to the question about that.
Yes, which here should not should become obsolete in a sense because of the choice situation. Actually, I have a guess about which I think fits well with this. That if one formulates comprehension categories as a form, then it should be true that comprehension category is univalent, more or less if and only if the category is univalent and the comprehension category is full comprehension category. And then the rest completion comprehension category should replace general comprehension category by an equivalent full comprehension category. And then it should be possible to see that all kinds of structures like pi structure and all this stuff can be formulated in terms of folds, and so they're equivalent. When they're formulated in this weak form, they're equivalent with respect to this equivalence. Anyway, there should be kind of a cool folds formulation of comprehension category.
Okay, I will try and figure it out.
So you mentioned that part of this was formalized, so what did you formalize?
So that is actually in the last part when we give the definition of what a univalent false category is. That part is formalized in Concord part.
But do you actually have a language for false?
No, well,
You said it in case of categories.
in case of categories, so we have just one, we have a fixed measure, and then we do everything in, like you can embed this dependently typed language of false is a sub-language in some sense of univalent foundations. So you can just embed it into univalent foundations.
When the dependency category is finite.
And the dependency category is finite.
So that's like higher order abstract syntax.
No, I mean, I can simply, everything that I wrote here somewhere, I don't know where I wrote it. Here, I can just write it in univalent foundations. This is the embedding in some sense.
But you don't have a separate language.
No.
Thank you.
In principle, it's formalized, not formalized in a separate language.
It would be nice to also have that.
Somehow we should have this one-way categories are very cool because somehow we should have something like co-inductive types for this kind of gadgets. So like the simplest infinite one-way category is when one has arrows which stop at some point but go infinitely back, and then this is implemented in type theory as what's that called? Spreads? No, they're not streams. I think it's called spreads. It's when there is a type, and for every element of a type, a type.
Towers?
Well, I call it towers, but I think there is Andrew Bauer is not here yet, but he knows the name for it. I think it's called a spread.
Yeah, I think that's what Bear Martin would call them.
Yeah.
And this is the simplest
With
case,
events on it.
but the rest of them should also be. We played with some others, like the globular set is another example of one-way category, and it's also implementable through a co-inductive type. And in general, any such things should be implementable. But,
just to maybe be more specific, what can be implemented as a co-inductive type, at least for spreads and streams and globular sets, is the models over these one-way categories, the really pre-sheaves on these one-way categories.